Hi, so this is a small lecture video about thinking about electric charge and energy. So it's something of an introduction to thinking about energy. So energy is a concept that you would have already heard about in a previous class. It comes up in the context of mechanics. And the way that energy is often sort of introduced is by talking about various forms of energy and how you would go about changing the values of the energy. So the way that you change energy is you use work. So work is the quantity that I want to think with first. So work, W, has a simple definition. It's in the context of vectors, right? So force is a vector and displacements are vectors. So the work done by a particular force, if it is able to move, say, an object or operate over a displacement delta x, the work is simply this dot product. It's a vector dot product. So it's defined in terms of a vector operation, right? But if you look at the result of this, there's two things you can say really quick. It's a scalar. That is, the result of the dot product is a number. And in particular, the units in this case, right, are the units associated with newtons times meters. And the Newton meter is the same thing as the joule. So this is got energy units. Okay, so that's a little review on the idea of work. So in the context of electric charges, though, we might wonder how much work, right, is required to push two positive charges closer to each other, right? So what I mean by this is let's imagine a particular scenario. So here is a positive charge, and we can call it Q1. And here is another positive charge, and we can call it Q2. And the idea is we want to maybe start them off at, say, some initial distance, right? So D1, and so that's the distance between them, right? And you know that these two things repel each other. So the question is what if I wanted to take Q2, for example? Doesn't really matter which one, or I could do both. And I imagine moving Q2 a little bit closer to some new value of the distance. Oops. D2, or maybe D final, or some, symbolism. But the point is like, how am I going to calculate, right, the work required to do this? So in order to have a lot of control, right, let's set ourselves up with a very carefully described problem. So hold Q1 still and move Q2, right? So let's do that. And also we'll stay along the x axis, right? So we had a slightly generic problem where Q1 and Q2 are on some diagonal, right? So so now though, so that we know what to calculate and how to think about stuff, let's make ourselves have a very particular problem that's sort of easy to imagine calculating for. So that's what I've done here. So we could say that we start with Q1 here and Q2 way over here, and there is an x-axis like this, and let's put Q1 at the origin. That's pretty easy to imagine. And let's say that Q2 is at x equals to, say, x initial, right? And then the final situation, some number of hours later or seconds later, or it's just afterwards, right? After the work is done, I've got this situation instead. So Q1 is still in the same position, but Q2 is closer. So along the x-axis, Q2 is at some final position, right? So maybe instead of start, right, because I'm using initial, let's call this the initial configuration, and this is the final configuration of the charges. And the idea is the work is what caused the change, right? The work done is causes this change in configuration. So I'm going to do something for fun. Let's imagine that there's actually, right? So remember we said we're going to hold Q1 still and move Q2. So let's imagine how we might do that. And so just for fun, I'm going to say that Q1 is held still by a person over here, and Q2 is moved closer by another person over here, right? So it could be people, it could be machines or whatever, but something is going to need to do the work, right? And so this person over here, person number, say, A, person A is going to exert a force, right? And this force is acting only on Q1. But you notice that Q1 never moves. So what this means is that the displacement of Q1 is equal to 0. So that means that the work done by person A is only ever going to be 0, right? Because person A, although they're exerting their force, they're not causing any displacement. The displacement is 0 by person A. So there is no work done by person A. But person B over here, I'm going to call them a special name. I'm going to call them EXT. So person B is known as EXT. EXT is for external. So person B supplies what's referred to as an external force, right? And this external force is going to operate over a displacement that is not 0, because we start at some x initial and we end up at some x final. So we fully expect the work by this external person, right, person B over here on the right, is definitely not going to be 0. So let's calculate this, right? So we have to think a little bit though, right? Because the work done by this external force is equal to the force supplied by that person dotted with the displacement delta x. But the question is what value do we use? Right? So remember that what the person needs to do is they need to basically accomplish the task of overcoming the force on charge Q2 by Q1, right? Remember our problem, we've got Q1, Q2, and Q2 is being pushed away, right? This is the force on Q2 by Q1, but the external agent, actually I wish that, yeah, so I think you can tell. But the external agent needs to push inwards, right? So this is the force by the external agent. And you can see that as Q2 gets closer to Q1, F external needs to become stronger, right? And what this means is F external varies along the displacement. So we need to think a little bit more carefully about the work, right? So instead of writing that the work over the displacement is written this way, we're going to change our mindset a little bit, and we're going to not imagine, we're not going to imagine large delta displacements. We're going to imagine really small calculus displacements, right? So these are small displacements, vector displacements, but in the calculus sense. And all we get from that is small bits of work. And over this small displacement, the force that's being supplied is basically constant. And in order to know the total work done by our external force, we just need to add up all of the small efforts. We have to add up all the small amounts of work done along the full displacement, right? And so what this looks like, if these are the small amounts of work done, they're F dot dx's, we need to do this. Okay, so here's our problem. The work done by our little external person right here, right, as they force charge Q2 closer and closer and closer to charge Q1. Notice again, this person over here on the left is not able to accomplish any work because there was never any displacement of Q1. So we're only displacing Q2. Okay, so here's the work done. And the external force, which had to get stronger and stronger and stronger, what it needs to do, so let's be really careful, the external force needs to point towards the left because it is counterbalancing the force on Q2 because of the electric repulsion from Q1. So the idea here is we're just going to ask that the person, the external person, just supply the opposite of the force by Q1 on Q2. And if we do that, then these two arrows are the same, right, in terms of their strengths, but they are opposite in their direction. So this is how we say they are opposite in direction, but of the same strength. Right? So if I want this to be the case, right? So the force by Q1 on Q2, I'm going to, because electric field is a fundamental thing, let's do this in terms of the electric field. So I'm going to say that this is minus Q2 times the electric field of Q1, right? So remember, in terms of electric field, Q1 fills the space everywhere. In this example, Q1 fills the space with electric field, and Q2 feels that electric field. So we'll write it this way, right? So the external force that's required in order to do this is equal to negative Q2 times the electric field of Q1. And the electric field of Q1 points right, over at the location of Q2, it points up the x-axis towards the right. So this is negative Q2 times K Q1 over the distance squared times I hat. Right, so I've got a negative sign, I've got a positive I hat over here, and I have the 1 over 4 pi epsilon naught K value, the charge Q1, because I'm talking about the electric field due to Q1. And then this describes where Q2 is, right? Q2 is x away from Q1. So now we have an integral that we can do. The work done by this external person is equal to, remember, it's the external force dotted with displacements, small displacements. And we're going to start at a place called initial and finish at a place called final. And when we write it in terms of how we've written the external force, it looks like this. It's going to be a minus Q2. And actually, let me start this over again. So I've got a Q2. So right, there's the Q2 factor. And then I'm going to write the integral, right? So it multiplies the integral of negative electric field due to Q1 dotted with displacements that are taking me from the initial place, right, Q2's initial location, to Q2's final location. For us, what this looks like, right, is since the initial location, the final location, and the path between them is all along the x-axis, this just looks like Q2 integral from x initial to x final, right? These are two values of x, where x initial is further away, right? It's a bigger value than x final because we're causing them to get closer to each other. And then I've got negative k Q1 divided by x squared I hat, right? And then dx I hat with a dot product. Right? Remember, dx is a vector. So here is the dx vector. We're going to walk along the x-axis. So x-axis is I hat directed. And when we go from x initial to x final, actually, the dx values, because x initial is bigger than x final, the dx values secretly are actually negative because they're walking us backwards, right? So we'll walk backwards with positive I hat direction, which means we're moving leftward. So this is correct. Okay, so if you do this integral, you're going to get Q2 times, so the integral of negative 1 over, so don't forget, so we've got I hat dot I hat, that's plus 1, right? And then, so when you do the dot product, the result is we'll go from x initial to x final. We've got a minus kq1 over x squared dx, right? So this is the result of doing the dot product. And then we've got q2, we're multiplying by, so the result of this integral, right? So negative 1 over x squared dx, when you integrate it, becomes positive 1 over x. And we have to remember to evaluate from over the bounds. So this is Q2 times KQ1 over, right? So you do the evaluation at the end point minus the evaluation at the starting point. Like this, right? And this is the answer to how much work did the external force do. So I'm gonna change this a little bit. And I'm going to do something interesting. And actually, it's got to do with basically the sort of main point of this topic. So I'm going to take this external work done, and I'm going to redefine how I understand what the work does. So this external work causes a change in the potential energy associated with the charges, right? So we're going to identify that the external work is the reason why potential energy, electric potential energy, can change, right? So that's one thing, right? So we could go up in here and say that this actually is the change in the potential energy. Let me make that a little neater. So the change in the potential energy was caused by our external force, right? So our system's energy can change, where the system is just the two particles having a repulsive interaction. So the energy of that system can change because an external agent added some energy in this case. But I'm going to go a step further and do a little bit of definitioning. So we've got that delta U. If I were to divide by that charge Q2, right? I left it out front on purpose. So this is the potential energy per charge, if you think about it, right? Potential energy per charge. I'm going to define this as something called the potential. I'm going to define it as the change in potential associated with Q1. And this is right here, right? Because delta U over Q2 is equal to K Q1 over X final minus K Q1 over X initial. And we'll say that this thing in brackets, right, K Q1 over X final minus K Q1 over X initial is the difference in potential around Q1. You notice that everything is written in terms of Q1 now. I've sort of hidden Q2 because now I'm talking in a per charge basis. So I've hidden Q2. And I have this thing called the potential difference. And in particular, this potential difference around Q1 is the potential due to Q1 at the final position minus the potential due to Q1 at the initial position. And so we've defined something called the potential difference. So let me type that. We just defined a new quantity. Oops. Actually, let me put it a little lower. So we just defined a new quantity called the potential difference. This is the potential difference right here. And it is, so the potential difference in a sense, it belongs to charge. And actually, I'm not going to pick a particular charge, right? That says belongs to a charge, but it belongs to a charge distribution. And you'll see situations where you have problems of finding what's the potential of a particular charge distribution, right? So this potential difference belongs to a charge distribution, and other charges can feel it. Or you might say that somebody like F sub ext, right, the little external force that did this work, this little guy right here has to do work in order to move a different charge, Q2 in this case, around in the potential of Q1, right? So this is, so we just defined the potential difference. We understood it in terms of work required. You notice that the definition of the potential only ever depended on the electric field, as well as imagining places in that electric field, right? And so, this is the potential difference of charge.